Everyone has it. Okay.
Okay. So, yeah, tell me what you found.
Okay, Liza, can you go?
Oh, and yeah, and state, let me know who I'm talking to.
Okay, move. There you go.
Okay, we're at the start of your show. Okay, so to reboot,
Wait a
we were
second,
talking
I'm not
to
looking at you, that's what's happening. Well, I'm on the wrong screen. There we go. Too many. Okay,
and we have a whole lot of the team here, many experts.
right.
An introduction to you, so you know who everyone is, and talk a little bit about the new report and the new findings.
So Rick, right?
Yes.
Yeah, we have a little about all the executive summary and the bullet points on it about that. So I'm Paul Newman. I'm currently at the University of Maryland, Baltimore County, and I'm one of the co-chairs. So can you start that? So I'm hoping you can see this slide. Oop, nope.
I can, right.
The previous one.
So report was released about minutes ago or so. You can see the cover of the report. Win, who raise your hand, Win Chan, and say something.
Hello, I'm Yunqian and NOAA CSL.
And the camera is just in the center, everyone. So just if you wave at it.
You wave at it. And so Graham, University of Leeds.
Yeah, hi, I'm Graham Mann from University of Leeds on the aerosol science.
And then hello. And you can see our affiliations there. And Rick,
yep.
That QR code has the direct link. Is the executive summary and the highlights are in.
Okay, I'm having trouble hearing. I think we have I'm going to turn off my video and see if that improves the bandwidth.
Okay.
It may not, but
the owl is.
Yeah, it's the owl. I think it's.
Okay, so now I'm just a name, but I'm here.
Okay, so again, Paul Newman.
Yunqian Zhu.
Graham Mann, Leeds, UK.
And Bill Randall.
Okay, Rick, the QR code that you can see there, you can either URL, the report just went online. So you can find the huge report. It's got the executive summary and the highlights in it, and the QR code works also.
Okay.
The next slide. Just a few details about what we've done. This has been into the. So there was over 150 scientists that contributed to this from across the world. I believe 19 countries, if I'm recalling correctly. 21 countries participated. Next slide. The first chapter, 22 Hunga Eruption, and Simon Karn. I think you're gonna have to come up to the table, Simon. And Anya Schmidt were the two lead authors. So say something, then I'll see you. And
yeah, hi, I'm Simon Karn from Michigan Tech. I was leading in the first chapter, and yeah, co-author was Anya Schmidt, who's not here.
If you look, there's a couple of highlighted bullets for each chapter, right on this slide, but we won't read them. We presume you can get next chapter 2. The 2022 Hunga plume, the first month post eruption, and we have two authors.
Hi, I'm Lizzie or Elizabeth Asher from University of Colorado, and my co-author Bernard Legrand is not here today.
And from the University of Paris. Okay, next slide. The third chapter is the atmospheric transport and evolution of Hunga water vapor and aerosols, and unfortunately, Sergei Akakin and Barasa couldn't attend, but we have one of the co-authors here.
I'm Valentina Aquila from American University.
Thank you. Next slide. The fourth chapter is Hunga effects on stratospheric temperatures and circulation. And
hi, I'm Xingyue Wang from
And my co-author is Larry Coy from NASA. He's not here today.
Okay. And next chapter is the effects of the Hunga eruption on stratospheric ozone and related gases.
The University of Boulder, and my co-lead author is Michelle Santee from JPL.
Okay. And then thermosphere.
Hello, I'm Professor Corwin Wright. I'm Mike Jayu at NASA.
Okay, and the final chapter is the radiative forcing and climate. And I think Mark and Gary, you have to come to the table here.
From King Abdullah, University of Science and Technology.
From Science and Technology Corporation in Maryland. Okay.
And then this final slide is the people in the you can see the top is the 4 co-chairs here, and others and people who are present in sort of these are the people related to the chapters who are in the room here today.
Okay.
So we don't we didn't have a set of explicit bullet points. We were presuming you'd be able to read that document. So
yes.
Sorry, we didn't people online. But I think we can kind of go around and maybe people can speak to their particular things that we want to start with the co-chairs and then we can walk through the chapters. So
Sure.
Graham, why don't you start?
Oh, okay, yeah, I think you know, when the volcano erupted in January 20, you know, it really triggered a lot of interesting science. The explosivity of was really unprecedented and on the scale of crack, actually, in terms of its in terms of the energy of the explosion. And as was on the bullets there, then the altitude at which reached and the waves from the explosion in days, then it became quite clear this was an unprecedented event, and that's really what triggered the towards this being the first time I was reflecting about this report in terms of there really hasn't been a volcanic eruption on the scale that would trigger a kind of cool, and so I just thought I would, if I was going to say, I think that, you know, the fact that it was on that scale, and you know the different ways in which has affected the atmosphere is really what's brought this group together. The potential for substantial global cooling from this and the potential impacts on the ozone layer, then those are the sort of 2 main focus areas that sort of meant that it. I don't know if the other 3, Bill or Yunqian.
I might say there was a lot of individual activity, research going on initially in the first 6 months. In addition to people going to try to measure the plume, but people were trying to model it or something. And so the idea of our coordinated activity was to have some system model studies and systematic studies. They try to make a community assessment. So that's, and one key part was this research on the ozone effects on ozone was intended to be directly input to the.
Yeah, well, I'll just after immediately excitement about Hunga in the first week because everybody recognized the huge explosive nature. And there was a lot of concern about what might happen because of discussion of potential large ozone losses. Hydrogen in the stratosphere can reactive or source species that can lead to ozone depletion. There was a lot of concern about what might happen in the Antarctic ozone hole. In addition to the surface radiative effects and surface temperature changes. So there was a lot of concern about that. And it was great that this community got together to talk about that. And I think in a lot of ways, it wasn't really as dire as we thought it was going to be. But
Can you take a pause for a minute? We'll restart, okay?
Okay.
Wonder if you got any of that.
So what we'll do next is just go through the chapters 1, 2, 3, 4, 5, 6, 7. And I think if you come sit where I am, just come sit where I am to maybe speak to the principal bullets that are.
Yeah.
Not you.
Taller and taller.
Yeah, hopefully you can still hear me. Whoops, I'm muted.
Well, but because I'm right here, your video will be, and I think the
video.
Yeah.
Way to be seen and to be heard by the having trouble with the mic.
I think it's the Wi-Fi.
Switched it back. Is it still breaking up?
It was 30 seconds ago. Give it a try now.
Okay.
Nope, you just broke up.
Well, I think that's the best we can do. I'm not sure what's going on. I'll ask AV, but.
Oh, I've got you now.
Better now?
Yeah.
It might be picking up a little ambient noise from the room too. The mic doesn't filter.
Right. You could tell them to turn up the gain though. You're very quiet.
See if I can do that.
In any case, Rick, I don't know if you heard this is Paul Newman again. I don't know if you heard what I said, but I had remarked that there was a lot immediately about what it was going to do long term. And long term, we found that it wasn't nearly as severe as what we thought it was going to be in terms of ozone depletion and surface radiative forcing. But nevertheless, it had some fantastic results. So we're going to kind of walk through. We'll bring people. And so when you come up and your affiliation.
I can add just one thing to what you said there before, just in terms of, the water vapor that was released, the water vapor is a strong greenhouse gas, and then as well as the potential for ozone impacts.
Right.
That release of water vapor was kind of realized was going to be there for the next few years, as half of it is still up there in the stratosphere. And then it turns out that the fact that it was so explosive, the altitude at which the water vapor was released, meant that its surface warming effect from that extra water vapor much weaker than it would have been if it was the tropopause. Some early papers that came, the fact that that kind of the water vapor uniformly, and it turns out the altitude at which the water vapor was released was a key thing as to why. But I won't use up any more time on that. But I think the climate side, obviously we've had this period of record global warmth, and then any to would have added to that and made that much worse, made that worse. Then obviously it is of concern to the scientific community. So
Go ahead, son.
Yep. So, hi, can you hear me, Rick?
Yeah, sort of. It's still breaking up, but it's better than it was. I should be able to piece it together and read the report and get back to you guys.
Yeah, I'm Simon Carn. I'm a volcanologist. I was sort of on the team to provide the sort of volcanological why this eruption was interest to volcanologists, in addition to the climate and atmospheric scientists. So as other people have said, this is a highly explosive eruption, just a huge explosion, very powerful explosion. The most powerful explosion, the eruption of Krakatau in Indonesia in over a century ago. It was a large eruption, and volcanologists are interested in large eruptions because they're unusual, they're rare. We use a scale called the Volcanic Explosivity Index, or VEI, to measure eruption size, and it's a scale that goes from 0 to 8. The largest we in geological record. This was a 6, which is quite large, and it's about this kind of size eruption we expect to see on average 1 or 2 times a century. And the last one before this was Pinatubo in 19. So it's a very large eruption, so immediately interesting from that respect. But it was it's different from other eruptions because it was a submarine volcano. First eruption from a submarine certainly in the observational record. We don't know when the previous one before this was kind of distinct. So the eruption water, so it's hard measure the volume of deposits. A little bit of uncertainty on the size of the eruption, but we know it created a huge crater, caldera underneath the ocean, which we can calculate the volume, size of the crater, so we know it was a very large event. But yeah, it was denoted a huge plume with shock waves that are immediately visible on satellite imagery, radiating around the globe, which other people will talk about later on. And a huge plume height. So when you 58 kilometers into the atmosphere, which is unprecedented observational record, that kind of plume height. Most eruptions, a lot of eruptions reach the stratosphere, but this is the first one, mesosphere record. But one of the unusual aspects was the emissions were kind of unusual because it was a submarine volcano. So there was an interaction between the seawater, which was responsible for the high explosivity. Probably that interaction is very explosive. We know that's it's the same kind of thing that happens in nuclear. It's very explosive. So that very explosive and generated this huge explosion, this huge plume, which in an observational record. But because of the amount of water in the eruption, the emissions are quite distinctive compared to other volcanic eruptions. In most volcanic eruptions, what we're from an atmospheric standpoint is sulfur dioxide, SO2, which is the main sort of climating agent in eruptions. Basically, the more CO2 that's emitted, the stronger the effect on climate. Usually, there's a cooling effect. The sulfur, the SO2 converts to sulfuric acid. Have reflecting sunlight, you get a cooling effect. But this was relatively low. It produced about 0.5 to 1 teragrams or million tons of SO2, which for this size of eruption was quite low. We were kind of expecting a little bit more, maybe. Pinatubo, as a reference, was more like 20 million tons, so an order of magnitude larger. This one was quite low, but it was water vapor. It was 150 teragrams of water vapor. So that sort of swamped the SO2, and most of the effects were due to the water vapor rather than the SO2 in this case. So it was interesting, and that sort of had a strong impact on the atmospheric and climate impacts of Hunga, were mostly due to the water vapor rather than the SO2. The SO2 had a sort of minor impact, and that was one of the the interesting aspects of this event. A lot of lightning, volcanic eruptions often produce lightning displays, and this would produce the most in Earth's atmosphere. A few decades, but sort of key, most interesting of this eruption as well, the huge amount of lightning produced, which is also probably due to the amount of water and ice in the plume, involved, which generated lightning in the kind of similar way to, a very large, essentially. So it's very interesting from a but sort of unusual. It's a very unusual event. It's one of the, we have this huge array of geophysical observations for this eruption, from satellites, from the ground, geophysical observations, which is just really great to it's a really kind of really advance our knowledge of this kind of just because it was so well observed from instrumentation and so forth.
So I've got two specific questions, if you can hear me.
Yeah, sure.
Yeah, you looked over, so I think you can. Is the reason for the low sulfur the source magma, or did the seawater filter it out?
The theory is that there's been some measurements of the sulfur in the magma, and it was quite high. The magma may have reached to the eruption of Pinatubo, so around 20 million tons, but most of that didn't reach the atmosphere. It dissolved in the seawater, or somewhere was removed in the seawater in the plume. Yeah. So
right. Okay, sorry. And did the lightning create any interesting things that made their way into the atmosphere like I'm thinking oxides of nitrogen or whatever?
Well, we would have expected that, but we didn't observe. There was no any major observations. I don't think of a huge NO2 or NOx. Usually you'd expect some lightning generated NOx, but it wasn't the case here. Maybe because of the water vapor, or maybe other people can.
It's curious why that didn't happen. That's only a minor outstanding question.
Okay.
So let's go to Lizzie next.
Hi, I'm Lizzie, and I'm one of the two lead authors of Chapter 2. I'm just going to reiterate a couple of key points from our chapter, most of which Simon mentioned. But this energetic eruption was very high altitude, so the overshoot reached about 58 kilometers altitude. And, basically the volcanic plume, both water vapor and a rapidly forming aerosol layer were observed above 30 kilometers and descended to about 26 kilometers a few days later, driven largely by water vapor cooling. About 145 or 150 changed the stratospheric water vapor budget by 10%. And although it was an amount of SO2, 0.5 to 1 teragrams that was injected from both space and balloons.
Okay. Now, water in the mesosphere does different things, right, than in the stratosphere. You said that earlier, but it broke up. Can you elaborate on what? Because I thought there's a level at which absorbing maybe it's carbon dioxide, but where it produces cooling, not heat.
Well, okay, so I think a later chapter will actually talk specifically about the.
Okay.
Carmen, you should take note of that.
And it was, although the overshooting top of the plume reached 58 kilometers, the vast majority of the water vapor only released the kilometers or so. So it did reach 58 kilometers, the eruption, but that was really this kind of, when you see in fact, on the front cover, you can see, the central kind of dot on the cover is the overshoot. You can see.
And what level did you say the majority hit that broke off?
30 kilometers.
Yeah.
Got it this time.
Go ahead, Valentina.
Sure. I'm Valentina Aquila. I'm one of the chapters. The lead authors are Sergei Kaikin and how satellite observations and also models show the transport of the water vapor and aerosol from Hunga. It's interesting in this because they kind of started more or less together, but they quickly separated vertically with the water vapor going up and the aerosol descending toward the lower stratosphere. And the fact that they were separated vertically also led to the transport. So with the water vapor going up through different channels, let's say both to the south, to the southern and to the northern hemisphere later on, while the aerosol stayed confined to in the southern hemispheres. After 2 years, both water vapors and aerosol were still in the stratosphere. The aerosol settle, let's say, was faster than, was eliminated, let's say, faster than the water vapor. Interestingly, satellites all agree very well in terms of what the water vapor did, but instead they differ quite a bit in terms of what happened to the aerosols, in the sense that satellite observations relies on assumption on particle size, and the aerosol particles generally larger from what is expected in like non-volcanic years or even in other volcanic events due to the presence of waters, which is also shown by the models. Models also do pretty well in simulating the water vapor and do relatively well in simulating the transport of the aerosol, but also struggle a little bit in reproducing how the radius of the particle.
So you're saying the aerosol was larger particles? Is that what I heard?
Larger particles than what so it grew to larger particle pretty fast because of the presence of water.
Okay. So what is the impact of larger particles versus smaller? It seems like it would reflect less per gram.
Right, and they absorb more in near infrared. I think there's another chapter that cover that. When
So there is a optimal size of particles that can reflect 0.3 to 0.4 micron, which is actually what Hunga aerosol is grow into. So Hunga aerosol is very effectively reflecting the sunlight compared to.
So it grew at about 0.35 microns in the observation, and kind of while settling down in the stratosphere. So for the whole 2 years, it was about the size of 0.35 microns. So,
Okay, why don't we switch to chapter 4?
Hi, this is one of the co-lead for chapter 4. In this chapter, we looked at the Hunga effects on strand circulation. So Hunga left a very fingerprint on the stratospheric temperature. So I really want to highlight this figure. I don't know if you can see.
I'll have to look at the report. It's too blurry. I see squiggles.
Right. That's the multiple lines here just show you the temperature anomalies. So here just look at the hunger related anomaly and compare them with the long-term stratospheric temperature. So hunger behaves very differently than all the previous major volcanic eruption. For example, the Eruption, they caused the warming in the stratosphere. However, for Hunga eruption, due to the water vapor injection, it cools the stratosphere by around 0.5 to 1K Kelvin. And this cooling gets stronger when you go to the mesosphere. So actually, cooling anomaly increases with as the warming following the other previous volcanic eruption decreases with.
Okay.
What's the second highlight you can see in the Hunga highlights?
That's a third highlight figure.
Okay.
Yes.
So as long as I have you here, this may not be you. Are there ways that this can be traced to local weather impacts?
That's a great help me answer these questions.
Weather impact?
Weather impact.
I don't know.
So the surface, as I was saying, the surface impact.
Let's leave that to chapter 5.
But I want to highlight one minor detail, that the fact that this water vapor, we recognized earlier, the community did, that it was going to be for tracking the transport in the models, and that continues till looking at how the dispersion of the water compares to global models. And
Can you say that again, please?
as early as the transport of the water vapor from the fingerprint to use to discriminate transport in global models that have a resolved stratosphere. And the kind of the take home messages of the whole Hunga activity was that we can discriminate our models, and in particular for the water vapor for the transport.
Okay.
On the global scale transport.
And it partly comes back to this high altitude case. We haven't had and the water vapor kind of went within the deep of the stratospheric circulation. We've never really had the other volcanic eruptions, it's gone in the shallow branch, but in the stratosphere, this deep branch, because and he's really testing the model transport through into the mesosphere. And so, yeah, this is where it will remain a sort of a unique test for the model, so far unique to processes in the upper stratosphere.
I think the bottom line, Rick, is that the models we've found have transported the material quite well, getting it from the lower stratosphere to the upper stratosphere and dispersing it. It was 20 south that the eruption went, but that material was dispersed reasonably southward and northern hemisphere. The models I would give it's something like a B grade in moving the material around. It's quite remarkable how well the models transported things. Aerosols are a different. Let's talk ozone here.
Mm-hmm. Yeah, so hi, I'm Freya Østerstrøm. I'm at the Aarhus, Denmark, and I co-led the chapter chemical and composition changes. And so in the months following the eruption, we saw massive perturbations to several trace gases related to ozone, also ozone itself. And while a lot of these were driven by chemistry on the volcanic aerosols, a lot of these changes were dominated by the transport. And it's difficult to say how much of that transport was directly Hunga related.
Thank you.
And sort of in summary, all of these, some of them were large changes, particularly in the second half of 2022. They didn't have a major impact on the total column ozone levels. And the other point I want to make is that the eruption had no significant impact on the Antarctic ozone.
Yep, I saw that in your bullet point. Yes.
Yeah. Yes.
Okay.
Yeah.
Why don't we move around to the mesosphere side?
Absolutely. Can you hear me okay if I speak from here, Rick?
I think I can hear you better from there than I can from up front. So go.
I'm doing well. Fantastic. Okay. So I'm Paul Wright, as was mentioned, and I'm one of the two lead authors of Chapter 6. I'll be fairly succinct. Firstly, there was a very, very strong and fast response dynamically to the eruption. So that caused sort of massive shockwaves going through the atmosphere. That gave us a lot of fundamental understanding of how the atmosphere responds to sudden shocks. That's very important for long-term weather modelling in particular. Secondly, as was referred to several times earlier, there was a very significant increase in mesospheric water vapor of about 3 or 4 teragrams. That was primarily by upward transport rather than directly from the initial eruption. In the mesosphere, and that is slowly dissipating. The water's still there and will be gone probably in a couple of years.
Okay. And what are the effects of water in the mesosphere? I realize we're running low on time.
I am not a chemist, so I'll let someone else clarify.
Okay.
Yeah.
Well, it reduced the ozone. Reduced ozone ended up cooling the mesosphere.
Okay.
We see the biggest temperature change actually in the mesosphere, over a degree in global average.
But this is some of the science is focused on now is that we're in this later stage where it's gone up. What's remaining is to the mesosphere, and it is tested. It will test the models as this next couple of years.
The models are doing a very effective job. Yeah.
So the sync process will be a kind of a test for the models, and we'll learn more about the result.
Okay, so quickly, what does cooling the mesosphere do? I mean, I think noctilucent clouds and things like that, but what else does it do to the climate?
I don't know if you heard him.
There's a small decrease there's some decrease in the mesosphere, but if you actually calculate how much that changes the total column, which affects UV radiation, it's almost zero change, just a little tiny change. So the impact of the mesospheric ozone loss is really unimportant, but interesting scientifically.
But you asked about the temperature in the mesosphere, but maybe the same answer. I think
Yeah.
a 1K cooling in the mesosphere, I'm not sure of any.
It's probably within the error bar.
Yeah.
And after the Krakatoa eruption, actually, as well as being, in terms of this energy of the explosion for Hunga being at a similar level to Krakatoa, thought to have released water in its explosion as well. So to some extent, Hunga certainly more like than Pinatubo or El Chichon. And then your question about the noctilucent clouds, after Krakatoa, there is this association with increased noctilucent cloud several years after Krakatoa. That was a bigger release into the stratosphere, so we're not expecting to see that kind of effect. And that, but this association with the clouds is a research.
Main satellite measuring noctilucent clouds stopped early on. We don't have those global measurements anymore right now.
Yeah.
Oh. Okay.
So let's turn to chapter 7, the radiative forcing and climate effects.
We have to finish in 60 seconds.
Okay.
Okay.
Hit them with the big points.
Okay, let me just go. So one of the earlier reports and some scientific calculations that the increased water in the stratosphere would warm the climate. And it turns out that one of the big impacts of volcanic eruptions we've known for years is they actually cool the climate. What we found is the two cancel out to a large extent, so that the cooling associated with the climate actually was a little bit bigger. Cooling associated with the aerosols was a little bit bigger than the warming associated with the water in the stratosphere. So the net effect on the net climate impact of the eruption is pretty small, almost from a radiative forcing viewpoint. And so we've run a bunch of observationals. And we expect that the water vapor amount in the stratosphere will probably be gone by about 2030. It's a much more long-lived gas. The aerosols have already disappeared from that eruption. There's other eruptions, of course, Ruang and stuff that followed on, but the aerosol anomaly associated with Hunga is pretty much gone at this point.
Let me add to this. So volcanic eruptions usually produce strong impact. And in this sense, Hunga eruption could be put in the line with the strongest eruption 20th and 21st century, Pinatubo, because both of these eruptions produced very strong changes in the stratosphere. Pinatubo increased content of sulfur in the stratosphere by 2 orders of magnitude, but Hunga increased water content in atmosphere also remarkably by 10%. This is important to better understand how system reacts to this injections into the stratosphere, and it has relation to important research related to geoengineering and impact of nuclear on climate. Volcanic eruptions teach us will respond, and Hunga very interesting and remarkable event that has to be studied.
I have a hard stop. I'm sorry, but we will connect you with Rick for follow-up questions. Thank you all for coming.
Thank you.
Thank you. Thanks, Walt.
And thank you for putting up with the breaking up of everything.
Rick, we're glad you were able to come. Thanks.
And
Thank you.
thank you.
The room too.
Mhm.
Yes.
Thank you.
Graham?